Okay. Last speaker for our session is Victor Franken. He'll tell us about de Sitter connectivity from Entanglement.
Okay, does it work? Yeah. Okay, hi everyone. Thank you for being here, and thank you to the organizers for inviting me. Today my talk will mainly discuss entanglement and connectivity in de Sitter holography. So, so just in case someone got lost and ended up in the wrong room, this talk is mainly in the context of holography, in which gravity in a bulk space-time V is completely dual to a quantum theory defined on a time-like boundary of this space-time. And in the context of ADS-TFT, which is the most known example of holographic duality, a very useful tool has been the connection between geometry on the gravity side and entanglement on the CFT side. So this led to a lot of progresses, such as the subregion duality, black hole progresses in the understanding of the black hole information paradox. And the one that will interest me the most today is the emergence of space-time from entanglement in the CFT. So to illustrate this idea, I can take a simple example consisting of two identical CFTs, both dual to an ADS space-time, and try to construct states from these two CFTs. So the simplest one I could construct would just be a tensor product of the states of the left and the right CFT. And so in this case, the two CFTs are not entangled. They don't interact. They basically don't know anything about each other. And the gravity dual to this state is what you could imagine naively is just a tensor product of two ADS spacetimes that are completely disconnected. Now, what happens if I try to entangle degrees of freedom on the left and right CFTs? One way to do so is to define the thermophile double state, which basically couples eigenstates on the left and right CFT with some weight factor depending on the energy level. And looking at the bulk gravity dual to this state, one ended up not with two disconnected spacetimes, but instead with one connected ADS black hole. So here we still have the two asymptotic ADS spacetimes with the CFT defined on their boundaries. The two CFTs are completely disconnected. But now the two asymptotically ADS spacetimes are connected by a bridge, a spatial bridge, which is the interior of the black hole in red here. So to summarize the idea, by entangling degrees of freedom on two asymptotic boundaries, we can create some geometry in the bulk. And the goal of my talk today is to try to apply this idea in the context of de Sitter holography. So de Sitter has been discussed a lot today, so I won't get into too much details, but for now, the main things you have to remember is that a space-like slice of de Sitter space has the topology of a sphere, and this sphere is expanding in size. Because of this, any observer in the spacetime does not have access to the full spacetime. So in particular here, we considered two antipodal observers, so two observers located at antipodal points of this sphere, and the blue regions basically depict the region of spacetime that the observer can interact with. And this, so we call these regions the static patches, and they are bounded by cosmological horizon, which are the diagonal lines here on the diagram. So we want to talk about holography in de Sitter space. The main difficulty that has been already discussed is related to the fact that de Sitter does not have a time-like boundary. And so we can give, I think, three interpretations, at least, to this idea. The first one would be the most pessimistic one, is just to give up on holography in de Sitter space. There is no boundary, so just no holography. This is a bit unsatisfactory for many reasons, but one of them is that there are some properties of semi-classical gravity that are very general and supposed to be valid also in de Sitter space that are closely related to holography, such as the covariant entropy bound, for example. A second possibility, which has been discussed a lot today, is the CFT correspondence, which basically, so the idea here is basically to give up on the idea that holographic degrees of freedom should be located on a time-leg boundary, and instead locate them on any boundary we have, the only boundary we have, which is located at null infinity, and it's space-like. It's a very interesting possibility, but I won't discuss it today. Instead, I would like to focus more on the third one, which I could consider as the simplest one, which would be to stick with the idea that holographic degrees of freedom are located on the time-leg boundary in holography, but there is no such boundary in the de Sitter space. So we have to accept the idea that there will be no dynamical degrees of freedom in quantum gravity describing the de Sitter space. So the idea that there is no dynamical degrees of freedom in the theory is a bit strange, although it's consistent with path integral considerations as well as the island formula. Though if we accept this idea, there's still a question to be answered, which is that we do live in a universe that is de Sitter-like, and we do observe non-trivial dynamics. So a satisfying quantum theory of gravity in the de Sitter space should be able to explain such non-trivial dynamics. And one way to do so is to explicitly include an observer in the theory. So physically, the idea behind this is that any meaningful observable in the de Sitter space should be measurable by an observer. So we have to somehow select the observer that make these observations, and choosing such an observer is implicitly equivalent to basically choosing a static patch. The thing is that we just saw that a static patch has an effective boundary, which is located at the cosmological horizon. So intuitively, at least, this leads to the idea of locating degrees of freedom encoding all the physics in the happening in the observable universe on the cosmological horizon that bounds it. So this is called usually static patch holography. So as written, I already said it, but the idea is that the state of the static patch of an observer, so the causal region of this observer, is entirely described by a quantum theory living on the cosmological horizon. So one of the nice things with it is that it gives a nice interpretation of the Bekenstein formula as a simple counting of the number of degrees of freedom of the quantum theory located on the cosmological horizon. And it's also consistent with the covariant entropy bound of Musso, but I think I don't have time to enter into this. So now that we are focused on static patch holography, one very interesting question, I think, is how can a closed and connected universe, such as the de Sitter space, can be described by a holographic theory which only describes an open and finite portion of this universe? Because at the end, the classical spacetime, at least that we know, is the de Sitter space, and not only like the solution that emerged from the equations of Einstein is a global de Sitter space and not just a static patch. So to answer this question, a very useful tool will be inspired by the Rita-Kanagi formula in ADS space, which basically relates the entanglement on the CFT side to purely geometric quantities on the bulk side. And the problem of adapting this formula to static patch holography has been tackled by Shagulian and Susskind a few years ago, which led to the monolayer and bilayer proposals. So these two gives nice results. For example, they recover the Bekenstein-Hawking formula. However, they have two main weaknesses. The first one being that they are only valid on the time symmetric slice because they don't take into account the non-trivial evolution of the de Sitter space. And they also don't take into account quantum correction coming from bulk fields. And we will see that it's quite important. So in the paper I'm discussing today, we tried to define a covariant holographic entropy description to compute entropies on this quantum theory defined on the cosmological horizon, which takes into account quantum corrections. So I try to summarize it in a few words. We start from some Cauchy slice in the bulk, which is here the dashed line. And the two cosmological horizons here, so the diagonal lines, naturally divide this Cauchy slice in three parts. So the left, right, and exterior part. They also define naturally the two holographic screens associated to this slice that we note SL and SR. And roughly the idea of the prescription is just to repeat some prescription that is completely analogous to the one we do in DS, but in these three blue regions instead of just one ADS bulk. And so these blue regions, I didn't say it, but these blue regions are just the causal diamonds of the three subsystems of this slice defined by the cosmological horizons. So to be just a bit more precise, if I consider some subsystem of the two screens, so the SL and SR, and that I want to compute this entropy, so here the subsystem is depicted by a red dot on the left screen, I look in each of the blue regions for a minimal extremal surface, minimal quantum extremal surface that is homologous to A. So by quantum extremal, I mean that it extremizes the generalized entropy, and by homologous, I mean something that's very similar to the ADS definition, which is basically that in some of these blue regions, the extremal surface I'm considering and A define the boundary of spatial subsystem in this region. So these regions are called C, and they're depicted by these red segments in the diagram. Once we found these three extremal surfaces, the entropy is given by the sum of the areas divided by 4G times h bar, plus the quantum corrections given by bulk fields on this red slice. Now that I defined how to find extremal surfaces, I would like to assume that entanglement wedges are something that should be very general in holography and not some specificity of ADS CFT. If I accept this idea, I'm led to the fact that the states of everything happening in these red segments should be completely encoded on the subsystem A of the quantum holographic theory. So with this, we have basically a duality between we can find, given some subsystem of the quantum theory, the subsystem of the bulk that's encoded on it. And now I'll try to quickly apply this prescription to simple subsystems. The simplest one that's non-trivial would be just the full holographic system, so the two screens. And this example is quite simple because in this case, in all regions, the empty surface, which is the set of empty points, is always homologous to the two screens. And it's also extremal. And because its area is vanishing, there is basically nothing that has a generalized entropy that's less than that. So it is always the minimal quantum extremal surface. And we find that the entropy of the two screens is vanishing. So the full holographic system is in a pure state as the Sitter space. And we also find that the entanglement wedge of the two screens cover a at least one complete Cauchy slice of the space-time. So in other words, the two screens not only encode their own static patch, but they also encode the region that connects the static patch. So this leads to the conjecture that not only the two static patches are encoded on the cosmological horizons, but the full space-time should be described by holographic quantum theory defined on these two cosmological horizons. And this is quite reminiscent of the case of the ADS black hole I was mentioning before, where we have initially two holographic screens on the cosmological horizon, both encoding a static patch. But once I take into account the full state, which entangle these two sites, I end up with a bulk spacetime that connects the two initial holographic screens. In particular, the region connecting the two static patches emerge from the entanglement between these two holographic screens, basically. And maybe I can, in a very short amount of time, discuss the second simple example, which would be to just take one screen and not the two, so one of the two screens, for example, the left one. What we find, at least at the classical level, is that the entropy of the screen is given by its area divided by 4G, which is exactly the Gibbon-Hawking formula. So it's consistent with this idea that the Gibbon-Hawking formula counts the degrees of freedom of this quantum theory defined on the cosmological horizon. The issue here is that at the classical level, the entanglement wedge is not determined. So in the exterior region here in blue, the extremal surface could be located basically anywhere on this blue line here. It leads to the idea that at the classical level, we cannot decide if the screen is able to encode something else that's in its own static patch. The question is, does the entanglement wedge goes beyond the static patch or not? And one way to answer this is to consider the first order quantum correction to the entropy. And what we find is that the degeneracy of extremal surfaces is lifted, and we end up with only two competing extremal surfaces, which are the holographic screens themselves. And what happens is that when the extremal surface is the screen itself, so as in this diagram, we end up with an entanglement wedge which only extends in the static patch. And when the extremal surface is located on the opposite screen, we have the left screen encoding its own static patch, but also the exterior region. And we have, there can be like phase transition depending on the Cauchy slice we consider. But in every case, there is at least one of the two screens that encode this region in the exterior. And maybe to conclude, in ADS-CFT, such situations where there are two competing extremal surfaces with a transfer of dominance are interpreted as a transfer of a complex factor in the Van Neumann algebras of the two screens we consider. So there is an entanglement wedge which is transferred from one screen to the other, and this entanglement wedge is always exponentially complex to reconstruct. So one interesting question would be to see if this ID applies to this case, to this de Sitter case. Thank you.
Questions?
Usually, if you consider a theory of quantum gravity, there's an issue with the Hilbert space factorization across a Cauchy slice. Mm-hmm. Is that playing any role in anything you're describing, or are you assuming that the Hilbert space factorizes?
So do you mean, is your question that I assume that the Hilbert space factorizes between these two screens? Yes, we don't enter into this, so we kind of assume that it's the case, but it's clearly an interesting problem that should be seriously considered. But I don't have anything precise to say on that.
Okay, thank you.
So for the generalized entropy, there's a path integral proof using the Euclidean path integral doing the replica trick. Can you at least define a replica trick that would produce your entropy in this space-time?
So at the moment, I don't have any, but no. So there is no at this stage. The idea is this covariant prescription is kind of taking inspiration from the static one of the monolayer and bilayer proposal, and the idea is just to try to find a prescription that satisfies some consistency check, like recovering the Wittgenstein-Hawking formula, finding that the entropy of the two screens is vanishing and all these things, while satisfying subadditivity, all these things. So there is a number of constraints that leads to this prescription, but it's not derived from a path interval.
Is it strong subadditivity that it satisfies?
Yeah.
Okay.
Yeah. But so that would be the next step to derive this from a path interval computation. But yeah, I expect it should be doable.
Okay. Thank you.
Any further questions? If not, then let's thank Victor and other speakers again. And